Hello students, in the previous class we studied refraction through plane surface. Refraction through plane surface means if there are two media, air and glass, then the interface separating the two media was a plane surface. Then you can call it as refraction through a plane surface. Instead of that, if the interface separating the two media is curved one, is curved, if the interface separating the two media is curved, then you can call it as refraction at spherical surface. Here the refraction is taking place, but the refracting surface is curved. Refracting surface is curved. What is that refracting surface? It is the interface between two media, interface that separates the two media. Then it is called as refraction at spherical surface. The example you can take is paperweight, a glass paperweight. The upper surface of the paperweight is always curved, and that paperweight is made up of glass. So the interface between the glass medium and the outside air medium is curved. So you can refer that paperweight as refraction at spherical surface. So in today's class, we'll see refraction at spherical surface and refraction by lens. Now we shall see what is these spherical refracting surfaces. Spherical refracting surfaces. So a spherical refracting surface is a part of a sphere of refracting material. So if this is a spherical refracting surface, if you complete a sphere using this refracting surface, if it is a spherical refracting surface which separates two media, then by taking this surface, if you complete a sphere, if you complete it, you are going to get a sphere. Then you can say this refracting surface is a part of a sphere. So why we say them as a spherical refracting surface? If you take the curveness of the refracting surface, if you take the curveness of the refracting surface, and if you complete its curveness, if you go on completing its curveness, you are going to get a sphere. That is why we call them as spherical refracting surface. Curved refracting surfaces are the part of a sphere made up of refracting material. So those are called as spherical refracting surfaces. If a refracting surface which is convex towards the rarer medium, the first diagram, this is the refracting surface which is convex towards the rarer medium, convex towards the rarer medium, then it is called as convex refracting surface. Then refer to the second diagram. If the refracting surface is concave towards the rarer medium, concave towards the rarer medium, then it is called as concave refracting surfaces. Concave refracting surfaces. Now here you can see, if you complete by taking this curveness of the refracting surface, if you complete a sphere, then the center of that sphere, the center of that sphere whose part is our refracting surface, The center of the sphere, whose part is our refracting surface, that center is called as center of curvature. Center of curvature. The geometrical center of the refracting surface is called as pole of the refracting surface. Pole of the refracting surface. Then the line joining the distance between pole and center of curvature. The distance between pole and center of curvature is called as radius of curvature of the refracting surface, spherical refracting surface. Now you can join a line, you can draw a line which passes through the pole of the mirror and center of curvature. If you draw a line which passes through pole of the refracting surface and center of curvature, then that line is called as principal axis. APCB. APCB is the principal axis. The same you can refer to a concave refracting surface also. Now when you take a small part of a refracting surface, when you take a small part of a refracting surface, then if you take a small part of a spherical surface or a spherical refracting surface, it is almost considered as planar. If you take a small portion, it is almost considered as a plane surface. Then the same laws of refraction can be applied at every point of this spherical surface. So the laws of refraction, the first law and the second law, that is nothing but Snell's law, both are applicable for the spherical refracting surface also. And sign convention for spherical refracting surfaces are same as that of the spherical mirror. Now, what all were the sign convention points? The distances are measured always from the pole of the refracting surface. The distances are always measured from the pole of the refracting surface. The second point is distances measured along the incident direction are taken as positive, and distances measured opposite to the direction of incident ray are taken negative. The third sign convention is heights measured above the principal axis are taken positive and below the principal axis are taken negative. So here we studied about only one refracting surface, one spherical refracting surface. Next we'll move on to the lens. Now, what is lens? Lens is a transparent optical medium. Transparent optical medium. How it is constructed? It is bounded by two refracting surfaces. It is bounded by two refracting surfaces, out of which at least one should be curved. At least one should be curved. So in the diagram it is shown. So if it is a one spherical refracting surface, it is another spherical refracting surface. So inside this, it is a glass medium, optical medium. Maybe it is this medium, maybe you can take glass, maybe you can take water, any optical medium we can take, but it is more convenient to explain with glass, so we are taking glass as a optical medium. So a glass is an optical medium having two refracting surfaces. So here both may be curved, or one is curved another one is plane. So it is having two refracting surfaces, out of which at least one should be curved. Then refraction is taking place at two surfaces, at first surface, at second surface. Then such a transparent medium is called as lens. Now, depending upon the shape of the lens, it is mainly classified into two categories. Mainly classified into two categories. So, lens is a optical medium bounded by two refracting surfaces. So, it is bounded by two refracting surfaces, two curved refracting surfaces. If the central portion, if the central portion of the lens is broad, if the central portion of the lens is broader than the edges, then it is called as a convex lens. If the central portion of the lens is narrower, central portion of the lens is narrower than its edges, then it is called as concave lens. Mainly it is classified into convex lens and concave lens. Again, in convex and concave you can subclassify. So in case of convex lens, if it is having two curved refracting surfaces, two curved refracting surfaces, then it is called as a biconvex lens. Bi means two. Two refracting curved surfaces are there. It is called as a biconvex lens. In that biconvex lens only, in that biconvex lens only, if the curveness of both the refracting surface is same, if the curveness of both the refracting surface is same, then it is called as equiconvex lens. Otherwise, it may be different also. See, one surface is less curved, another surface is more curved. One surface is less curved, another surface is more curved. This can also happen. Then you can say it is having two refracting surface, biconvex lens, but not equiconvex lens. If the curveness of the both refracting surfaces is same, then it is equiconvex lens. Now, among two refracting surfaces, one is curved and another one is plane. Then it is called as plano, as the surface is convex towards the rarer medium. It is called as convex lens. So if one surface is plane, it is called as plano convex lens. Plano convex lens. Now among two refracting surfaces, one is concave, another is convex, then it is called as concavo-convex lens. One surface is concave towards the rarer medium, another surface is convex towards the rarer medium. Then it is concavo-convex lens. In case of concave lens, it is subclassified into four types. As it is having two curved surfaces, it is called as biconcave lens. It is called as biconcave lens. Now, if the curveness of both the surfaces, if the curveness of both the surfaces in concave lens is same, then it is called as equiconcave lens. The curveness may not be same. Here it is less curved, here it is more curved. Then you can call it as biconcave, as it is having two refracting surface, but their curveness is not same. So you cannot call it as equiconcave. If the curveness is same, curveness of both the refracting surface, then you can call it as a equiconcave. concave lens. Now, among two refracting surface, one is plane and another one is curved, concave. Then it is called as plano concave lens. Plano concave lens. And if one refracting surface is convex, another refracting surface is concave, then it is called as convexo concave lens. Convexo concave lens. So these are the types of lenses mainly classified into convex and concave. Then, depending upon the curveness of both the surfaces, they are subclassified. Now we'll see how the lenses are formed. So here, while mentioning equiconvex lens, we have taken R and R. What is this R? In first case, biconvex, we have taken R1 and R2. But when it comes to equiconvex lens, we have taken simply R and R on both the sides. It means the radius of curvature of both the spherical refracting surfaces are same. Now what is this? Radius of curvature of a spherical refracting surface of two surfaces. So you can refer to the diagram. Here in the first one we have taken the convex lens. The convex lens. We'll see some terms related to the lens. So in the first diagram we have taken the convex lens. So inside the lens you can see O, that is nothing but optic center. So the geometrical center of the lens is called as optic center, which lies within the lens. So the midpoint of the lens which lies within the lens is called as optic center. Now the specification of that point is it is the point in the lens through which light ray passes undeviated. Even though light is traveling from one medium to another medium, when the light is traveling from one medium to another medium, air medium to glass medium, it is supposed to change its direction of propagation. But if it passes through the optic center, it passes undeviated. So that is the specification of the optic center. In case of concave lens, here is the optic center. Now, as the lens is having two refracting surfaces, one refracting surface and second refracting surface. If you take the curveness of those two refracting surfaces, you can complete two spheres. So let us take the curveness of this surface. Using this, you can complete a sphere by taking the curveness of the first surface of lens. You can complete a sphere. Again, you can taking the curveness of the second surface, you can complete a sphere. Then the radius of that sphere, which is completed by taking the refracting surface of a lens as its part, then the center of that sphere is called as a center of curvature of the refracting surface. Center of curvature of refracting surface. So this is the first spherical surface. So it is our first center of curvature C1. So it is in front of the lens C2. It is the second center of curvature. In the similar way, if you take the curveness of the spherical surface, curveness of the refracting surface of the lens, and if you complete a sphere, you're going to get the center of that sphere. It is called as center of curvature, center of curvature of the first refracting surface. Similarly, this is center of curvature of the second refracting surface. Now the distance from optic center to center of curvature. The distance from optic center to the center of curvature is called as radius of curvature. So the distance from optic center to first radius of center of curvature is R1, first radius of curvature, and the distance from optic center to C2, the second center of curvature, is taken as R2. So the lens has two radii of curvature, R1 and R2. It is because its two refracting surfaces are the parts of two spheres. Now the line joining center of curvatures and the optic center. If you draw a line which passes through the two center of curvatures and the optic center, then that line is called as principal axis. The line passing through the center of curvatures is C1 and C2, and the optic center is called as principal axis. Now, another term related to the lens is principal focus. So you all have come across this word principal focus while studying the mirror. How do you define the principal focus in case of mirror? When parallel rays parallel to principal axis are incident on a mirror, they reflect and meet at a common point. So there, in case of mirror, it was a reflection. Here, in case of a lens, it is refraction. So when paraxial rays are incident on a lens, then they refract. How they refract? After refraction, they actually meet at a common point. They actually meet at a common point, or they appear to diverge from a common point. Where that common point is, where it lies? It lies on the principal axis. Then that point is called as principal focus. So you can refer to the diagram. So here is the first one, a convex lens. Convex lens. The rays are parallel to the principal axis. Rays are parallel to the principal axis. So the center one, you can see it is passing to the center of curvature, sorry, optic center, it is passing undeviated. The two rays are getting refracted, means they are changing their direction of propagation after passing through the other medium. So after refraction, they are meeting at a common point in case of convex lens. In case of concave lens, these are the incident rays. So the center ray, center one ray of light is passing through the optic center, it is passing undeviated. The two rays, after passing through the concave lens, they are refracting. How they are refracting? They are getting diverged. They are not meeting each other at all. But when you look at their direction of refraction, their direction of divergence, when you extrapolate the refracted ray, their directions, they appear as if they are diverging from point F1. They appear as if they are diverging from a common point. So that common point is called as principal focus. In case of convex lens, after refraction, actually the rays meet on a common point. But in case of concave lens, after refraction, they diverge. But how their direction of the divergence is? The refracted ray are extrapolated back. They appear as if they are diverging from a common point. That common point is called as principal focus. Now the distance between the optic center and the principal focus, optic center and the principal focus, is called as focal length. So the distance between optic center O and the principal focus is called as focal length. So here you can observe for a lens there are two principal foci, f1 and f2, for a double convex or a double concave lens. Why it is so? So here if the ray is incident on one side, they are meeting at a common point on the other side. If the ray is incident from this side, they are going to meet at a common point on the other side. So this is also called as principal focus. It is also called as principal focus. So the lens is having two foci, f1 and f2. Now, how do you mention them as f1 and f2? Which one has to be taken f1 and which one has to be taken f2? See, the focus on the side of the source of light is called as the first focal point. The focus which is on the side of the source of light is taken as first focal point. See, refer to this diagram, first diagram. So here are the rays of light. It means somewhere here the source is which is emitting the light, and after refraction the rays are meeting at this point. So the focal point on the side of the source is called as F1. The focal point on the other side is taken as F2. That is what I have mentioned, second principal focus of the convex lens, F2. In case of concave lens, here is the source which is emitting the light rays. After refraction, the rays diverge, and where the refracted rays direction meet when they extrapolate at f1. So this is taken as f1. On the other side it will be f2. Now we'll see the image formation by the lens. What is image? Image is a point-to-point correspondence with the object. It is a point-to-point correspondence with the object established through refraction. Now object is emitting the light rays. Those all rays will be incident on the lens and they refract. After refraction, wherever those all refracted rays meet, that point is called as the image. But in principle, we can take any two rays emitting from the object for the image formation. It doesn't mean that only two rays are getting emitted. Number of rays will be getting emitted from the object, but only two rays are sufficient to show the image formation diagrammatically. But it is convenient to choose any two of the following rays. So the first ray that you can consider for the image formation is the ray parallel to the principal axis of the lens. If the ray is parallel to the principal axis, Then after refraction, where it passes through? It passes through the second principal focus in case of convex lens, but appear to diverge from the first principal focus. See here, if the ray of light is parallel to principal axis, after refraction it passes through second principal focus, or in case of concave lens, if the rays are parallel to principal axis, they appear from they are diverging from first principal focus. So this is the first ray that you can consider for the image formation. The second one is a ray passing through optic center of the lens. It emerges without any deviation. In the same direction it comes out. The third ray, invert of the first one. A ray passing through the first principal focus for convex lens or appear to meet at second focus. They emerge parallel to the principal axis after refraction. If you take the rays like this, they are emerging from the second principal focus. Then after refraction, they become parallel. So if they are passing from the principal focus on one side, after refraction they become parallel to the principal axis. So among these three rays, two rays are sufficient for the image formation. So in the next slide we'll see the image formation by considering these three rays. Image formation by considering the above mentioned three rays. So for that we'll consider a convex lens. So whenever you draw a convex lens, your first job is to mark the optic center, draw the principal axis, mark the points such as F to F. On the other side also you can mark the focal point and 2F. So here we are taking the object at 2F. So we can consider the rays as mentioned above. For the image formation, the first ray that you can consider is parallel to the principal axis. So after refraction it passes through principal focus. The second ray that you can consider is the ray passing through the optic center, passes undeviated. First ray the second ray you are passing through optic center, which passes undeviated. The third ray is, as this is our object AB we have taken, so rays we are taking from the point A of the object. So the third ray that we can consider is ray passing through the principal focus. After refraction becomes parallel to the principal axis. Now wherever these three rays meet is called as the image point of the corresponding image of the object A dash. So here you can get your image A dash, B dash. This is in case of a convex lens. Any two rays are sufficient among these three. Now we'll see the image formation by concave lens by using the same three rays. So let us consider XY as the object. Here is our concave lens, optic center. This is our principal focus F on one side and principal focus F1 and F2. First ray that we can consider is parallel to the principal axis. If the ray is parallel to the principal axis, It diverges. How it diverges? It's the direction of refraction. When you extrapolate, it appears as if it is meeting at a principal focus. So this is the direction extrapolated. The second ray that you can consider is the second ray that you can consider is the ray passing through the optic center. The ray passing through the optic center. So the ray passing through the optic center. This is the refracted ray. When you extrapolate the direction of the refracted ray, it is meeting here. So this is the point where the extrapolated first ray and second ray are appear to diverge from that point. Appear to diverge from that point. The third ray that you are taking is its direction of incident is passing through the focal point. If you look at the direction of the incident ray, as if it is passing through the second principal focus. So if that is the case, after refraction, it becomes parallel to the principal axis. When you extrapolate this third ray, that is also meeting at the same point. So here you can write x dash, the point, corresponding point for the x. So this x dash is not formed by the actual meeting of the refracted ray. It is not formed by the actual meeting of the refracted ray. How it is formed? By the meeting of the extrapolated directions of these refracted ray. When these all the three refracted rays are extrapolated in the backward direction, they meet at this point. It means the three refracted rays appear as if they are diverging from this point, as if they are diverging. So it is a virtual point. Then this image is called as a virtual image. X dash y dash is the virtual image of xy. This is how you can form the image by considering any three rays. Image by the convex lens as well as by the concave lens. Now we shall see the image formation by convex lens for different object distances. So the first possibility is when the object is at infinity. When the object is at infinity. So when the object is at infinity, the rays coming from the object will be parallel to each other. So the rays parallel to the principal axis after refraction meet at the principal focus. So when the object is at infinity, where the image is at principal focus. How the image is? It is real because the refracted rays are actually meeting. The refracted rays are actually meeting after refraction. So the image, you can call it as the real image. What is the size of the image? It is point image, or image is diminished. When you observe, it is an inverted one. So when the object is at infinity, you can say the image is real, inverted and diminished. Now from infinity we come a little closer, so that the image is beyond 2f. So the principal axis, we are dividing the principal axis as f, 2f and infinity, f, 2f and infinity. So we are keeping the object beyond 2f. When the object is beyond 2f, we are taking two rays. First one is parallel to the principal axis. After refraction, it passes through the principal focus. And the second one, you are considering the ray passing through the optic center passes undeviated. Optic center passes undeviated. Wherever these two refracted rays meet is called as the image. Then where is the image formed? Between f and 2f. Now the object placed beyond 2f, image is between f and 2f. How the image is? It is forming by the actual meeting of the refracted ray. Then it is real. It is inverted. Below the principal axis, it is inverted. And look at the size. It is diminished. Now again, we are moving the object little more closer to the lens. Earlierly, it was here beyond 2f. Now we are moving it little closer to the lens so that it is at 2f. Again we are considering two rays parallel to principal axis. After refraction passes through f, which is passing through C. After refraction passes undeviated. Now wherever these two rays meet is the image. Now the object is at 2f. When the object is at 2f, where the image is? At 2f only. It is formed by the actual meeting of the refracted rays. Then you can call it as a real. As it is below the principal axis, it is inverted. Now, what about the size of the image? It is same that of the object. Same size that of object. Now again, we are moving the object little close to the lens. Means between 2f and f. It was at 2f earlier. Now we are moving it bit nearer to the lens. Means from 2f we are moving it inside 2f, within 2f. Now when the object is within 2f or between f and 2f, again the same two rays here we are considering. The rays are meeting to form the image beyond 2f. So you can say for the object between f and 2f, image is formed where? Image is beyond 2f, beyond 2f. As it is formed by the actual meeting of the refracted ray, it is real. As it is below the principal axis, it is inverted. And look at the size compared to the object, image is larger. So you can say image is magnified. Now we are taking the object still closer between f and 2f. From between f and 2f we are taking it at f. So we are taking at f. When the object is at f, first ray is parallel to principal axis. After refraction it passes through the principal focus. The second ray is passing through the optic center. After refraction it passes undeviated. Now look at these two refracted rays. They are parallel to each other. If they are parallel to each other, they never meet or they meet at infinity. If the rays, refracted rays are parallel to each other, they meet at infinity. So you can say when the object is at f, when the object is at f, image is at infinity. Image will be at infinity. How the image is formed? It is real, because if at all they meet, the refracted rays only meet real and inverted, as it is below the real and inverted as it is below the principal axis. And how the image is, see, far away they are meeting means it is enlarged very much, real, inverted and magnified. Now in the next case, we are moving the object still closer to the lens compared to the previous case. So here we have taken the object at focal point. Here we are taking the object within focal point. Within focal point, AB is our object. Now the two rays that we are considering is again ray parallel to principal axis. After refraction, it passes through the principal focus. The second ray that we are considering is a ray passing through the optic center. look at their direction of Look at the direction of the refracted ray. They are getting diverged. If they are getting diverged, they never meet at all. So image cannot be formed by the actual movement of the refracted ray, because refracted rays are getting diverged. So as they move further, they cannot meet each other. Now when you extrapolate the direction of the refraction, extrapolate the direction of the refracted rays, the first ray and second ray, they appear as if they are getting diverged from this point. They appear, the two refracted rays appear as if they are getting diverged from this point A. So A dash is the image of the point A. Now you have to tell me whether this A dash is a real or virtual. It is virtual because it is not formed due to the actual meeting of the refracted rays. Here the rays have not actually met. Their direction of extrapolation is meeting. So this point is called as the virtual image of AB. So when the object is within focal length, within F, or object distance is less than focal length. So this is the focal length and this is our object distance. When the object distance is less than focal length, image is, how the image is? It is virtual. Image is virtual and it is magnified. Image is virtual and magnified for any object. It is beyond F, where it is formed beyond F. Now we'll see the image formation by concave lens. Concave lens. So this diagram already you have seen. We are taking an object xy. The three rays we are taking for image formation. First ray is parallel to the principal axis. After refraction, it diverges because the nature of the concave lens is to diverge the refracted ray. So the refracted ray diverges. How it diverges? Its direction, when you extrapolate, it meets at point F. This is the first ray. The second ray that you are considering is passing through the optic center. So it passes undeviated. So this is the direction of the refracted ray. When you extrapolate the direction of the refracted ray. Now look at these two refracted rays, the first refracted ray and the second refracted ray. They never meet. They are getting diverged from each other. Then it is not possible to meet those two rays. Then when you extrapolate their direction of refraction, they appear as if they are getting diverged from this point. They are getting diverged from this point. So this point you can take as the image of x. This point x dash you can take as image of x. Now tell me whether this x dash is formed by the actual meeting of the refracted ray. No, it is not formed due to the actual meeting of refracted ray. Then you can call this as virtual image. So wherever you place the object, in case of concave lens, the image is always between optic center and F. The image is always within the focal length and the image is always diminished in case of concave lens. Wherever you place the object, image is virtual and image is diminished, but not The same in case of convex lens. Sometimes the image is diminished. It is of same size. It is magnified. It is very much enlarged. When the object is at f and image is at infinity, the image size is very much enlarged, and it is magnified when it is placed within focal length. But in case of the concave lens, the image is virtual and always diminished for any object distances. Now you have to list out, looking at these diagrams, you have to list out, take it as a homework, U, V and nature of image. So when the object distance is infinity, where the image is formed at f, write the nature. When the object is beyond 2f, where the image is between f and 2f, write the nature of the image. So you have to list out u, v and nature of the image for different object distances in case of convex lens. Next, we shall move to the sign convention, because here also we are measuring the object distance and a sign has to be assigned to it. The first sign convention is all distances are measured from the optic center along the principal axis. See, if here is the lens, inside it the optic center will be there. We have kept the object, and after refraction here is the image formed. So distance from lens to the object is object distance from the lens to the object is object distance. But how the distances should be measured? From the optic center to the object. From the optic center to the object is taken as object distance. In the similar way, if you complete the sphere, here somewhere you are going to get C. Then from the optic center to the center of curvature is radius of curvature. The second point is distances measured along the incident ray are taken positive. Now which is the direction of the incident ray? Towards the right. What is our direction of measurement? Object distance towards the left. From the optic center to the object towards the left, as it is opposite to the direction of incident ray, u has to be taken negative. Again, in the same way, how we are measuring the radius of curvature? From the optic center to the center of curvature, which is opposite to the direction of the incident ray. So r is negative. Now what about the image distance? According to the first point, from the optic center to the image is image distance. From the optic center to the image is image distance. Look at the direction of measurement. It is in the direction of the incident ray. So V is taken positive. If the distances measured in the direction of the incident ray are taken positive and opposite to the incident direction are taken negative. Heights measured above the principal axis are taken positive and heights measured below the principal axis are taken negative. So object AB is above the principal axis, its height is taken as plus h. The image A dash B dash is below the principal axis, so its height h dash is taken negative. So this is all about the today's session, that is refraction at spherical surface, one refracting surface, the terms related to it. If there are two refracting surfaces, then it is called as lens, types of lens, it's a sub-classification. Some important terms related to lens and image formation by the lens. for various object distances. So go through the video and clarify your doubts in the doubt clarification session.